Good afternoon and welcome. I'm Ed Bogish. I'm the director of SyracuseCoE, Syracuse Center of Excellence in Environmental and Energy Systems. It's my pleasure and privilege to welcome you to our monthly Research and Technology Forum. Regulars will know that we usually do this on third Wednesdays at 3:30. So thanks for joining us a little earlier today. One of our speakers has an engagement on campus to work with students at 5:10. So we wanted him to be here for questions at the end. So we started a little bit earlier today. Our program of Research and Technology Forums is one of the elements of our partner program. If your firm or institution is not already part of our partner program, I encourage you to speak to Tammy Rosanio in the back, and she'll be happy to tell you about the benefits of the partner program. Also, we'll just take a minute kind of for the good of the order. We're working with a faculty member in the School of Architecture who's working with other faculty members in psychology at Syracuse University and also in architecture at RPI to study the impact of daylighting in the office environments on cognition. And this is a study that's actually looking for human subjects. The human subjects would spend a day in an office environment and your cognition would be evaluated. You'd be compensated for your efforts. It's $100 for spending a day as a subject, and there are openings tomorrow and next week. So out on the desk, there's a sheet that looks like this. It says "Help Improve Office Environments," and Tammy has them in the back of the chair. So if you're interested, so was there a question?
I was just going to say I participated in that. It's a wonderful experience.
Oh my gosh, she was like it's an unprompted testimony, especially the $100. So I also want to welcome to the Syracuse community John Liu. He's the new Vice President of Research. He started on September 1st. So this is day 20 of his new position. He comes to Syracuse from Auburn University, where he was an Associate Vice President or Associate Provost for Research. And we very much look forward to John. We welcome you to Syracuse. We thank you for, we know that you're being bathed with a fire hose in your first weeks at Syracuse, and we appreciate you making time to come and join us for this forum. And now it's my pleasure to introduce the moderator of this forum, Neil Webb. Neil is Director of Business Development at OBG. It's a firm that was previously known as O'Brien & Gear, but they've rebranded to OBG. Neil is the chair of our Industry Partner Council at SyracuseCoE. Got his undergraduate degree from Clarkson. He has an MBA from the University of Rochester. He's worked in a wide variety of positions in the energy industry and had really been in the, I don't know if it's the right place or the interesting place at interesting times, including at Niagara Mohawk at a moment of regulatory change that is very, very interesting. So Neil's got a background in engineering and lots of experience in understanding the financing of energy projects. And without further ado, I'm pleased to introduce Neil, who's going to guide us in this Research and Technology Forum.
I would never script my career. I never wrote that down. The winding around where I started and where I arrived throughout. So good afternoon and thank you for coming today. I have the privilege of leading and moderating this panel today in some areas really where I've had a lot of interest. One, from the power plant perspective of understanding exactly the byproducts or products of the technology of the combustion cycle for fossil fuels, most definitely, and the consequences that they kind of hold for us in the environment. But also from the policy side with trying to envelop and try to create policies that accommodate new technologies and new ways of thinking in terms of mitigating those circumstances that we've experienced over the course of time. The 90s was kind of a tenuous time with transition, and definitely with Clean Air Act and RGGI and a lot of the other initiatives that have been out there. So it's interesting, this type of work that Ryan is definitely working on. I can see that there will be a lot of potential success in these types of technologies getting out to the market and being commercially viable. There's a ready-made market for it. So let me start with trying to keep us on schedule. Ryan Falcon-Smith, who will be our first speaker today, is a PhD candidate in the Department of Mechanical and Aerospace Engineering at Syracuse University. His research interests include ion transport membranes and carbon capture technologies and greenhouse gas controls, which are something that's very relevant today. I want to let him get going because I want to also keep him on schedule. So I'll introduce Ryan. Please come up and share with us your presentation.
All right, good afternoon.
Good afternoon.
So, my name is Ryan Falkenstein-Smith. I work in a laboratory called the Combustion Energy Research Lab downstairs here at the COE. Today what I'm going to be talking about is an idea that breaks down into 4 different categories of motivation, why exactly it came about, the fundamentals of how it works, the projects we're working on in research environment, and then the outcomes of what that means of bringing these technologies to market. So the way a lot of people look at this kind of problem is they see power generation facilities that are mainly run by natural gas or coal are projecting a significant amount of carbon emissions into the atmosphere. At the same time, it's producing enough power to meet our demand that's steadily rising, but it's also causing dramatic shifts in weather patterns. So thinking about the perspective of a power generation facility, you start thinking about, well, you have to meet the demand, but you also have different policies that are put in place that mitigate the amount of carbon that you're emitting into the atmosphere. So how do you satisfy both camps? So that's where carbon capture for power generation kind of came about, is you're mitigating those CO2 emissions, but also at a minimized energy cost that's basically allowing the plant to still run, meet the demand, and also contain the CO2. So there's 3 different approaches to carbon capture technology. Pre-combustion mainly deals with an air separation unit and fuel that's reformed to only have combustion between hydrogen and oxygen, producing the only product of H2O. So carbon is essentially scrubbed out before the process, but you're still generating a significant amount of heat to actually generate power. Post-combustion uses these things called solvent beds to scrub out CO2 post-combustion. But it takes a lot of solvent beds, and there's a lot of other things that go on with that. Then there's oxy-fuel combustion. And oxy-fuel combustion essentially is containing the products of combustion during combustion. And it essentially breaks down into separating oxygen from the air, then delivering it directly to the fuel to generate heat and power, allowing the only byproducts to be CO2 and H2O that can be filtered out and contained or sequestered for use. So oxy-fuel combustion breaks down into a couple of different components. There's an air separation unit that requires the separation of oxygen from air, which is mainly made of nitrogen. And then you have the combustor, and then that filters into some turbine or power generation facility or power generation device, which generates enough electricity and contains heat. So there's a couple of different air separation units that are implemented for this technology. One of them is called cryogenic air separation unit. And essentially what that is, it's a system of compression and cooling air to the point where oxygen is filtered out, leaving nitrogen behind as well as some other products that are in the atmosphere. The problem with this is that it's energy exhaustive to do that because you're basically cooling something and compressing it to the point where oxygen just falls out of place. Then there's another technique called chemical looping combustion. And essentially what that does is it's a material or an oxidized metal that oxidizes in one atmosphere and then moves to another to combust. But the problem with that is if you start thinking about the material for repeated use, it's hard to ensure that the energy needed is the same every time, and it's hard to assure the material is stable enough to last for multiple repeated use, enough to actually combust. So we started thinking about these ideas and these approaches of compressing units and chilling stuff, and we started thinking about, well, what if we combined the advantage of both things? What if we compressed air and filtered it over some filtration system, which we call an oxygen transport membrane reactor, which transports oxygen through the membrane to combust with the fuel, in this case natural gas, in which heat is then collected either through the membrane itself and fed through a turbine, or heat from the exhaust is fed into another turbine to generate power. Well, that sounds like a perfect idea. I guess we can all go home, right? So this is called an advanced zero-emission power plant, and this is what I'm going to be talking about today. An OTM technology, how it functions, what we're working on, and what are its outcomes. So the fundamentals, how does this exactly work? Now this is, the basic breakdown is the material is highly catalytic at high temperatures. So if you know anything about ceramics, sometimes they have defects in them, and the more defects at higher temperatures is occurring, allowing it to react with oxygen to reduce it, become an ion. The ion then transports through the membrane and reoxidizes on the other side. Now, the only way this is going to be possible is if there's a chemical gradient or low oxygen on one side and high oxygen on the other that drive the diffusion of oxygen through that membrane. So there's a couple things going on. There's surface exchange, so that process of the material on the feed side interacting with the oxygen. Then there's diffusion, bulk diffusion, and then there's another surface exchange property in which it becomes oxygen again. So when I say oxygen ion, what I mean is it's taking on electrons and then it's giving them back to the material. And because of that, the material is actually charge compensated. So there's no need for external circuitry when you run these things. All that's happening is you're heating it up. And initially, all you need to really do is heat it up initially, and then the combustion from the reaction to sustain the performance of this membrane. So, like anything, there's limitations. Now, I know there's an equation in the middle, so if you're not really a math person, don't freak out. But the big things to take away from this are the surface exchange limitations as well as the diffusion limitations. So, right now, the way these materials work is you typically fabricate, you want to make sure the material is stable, it's mechanically strong, it can contain that reaction, and it's basically dense enough so it's going to filter out that nitrogen. So because of that, people make these really thick membranes because they want it to last, they want it to be strong. But the problem with that is that diffusion process I talked about, meaning that L value that you see at the bottom, as that grows, the amount of oxygen permeation, which is JO2, is diminishing, because there's a greater distance for oxygen ions to travel through the thick OTM. Now, there's another interesting concept that's now being introduced of nanotechnology. The cool thing about nanotechnology is you can make something really, really small, thin. Now, you can make it thin enough, so if we look at the right side, so that it's not limited by the diffusion, but now limited by the surface exchange on the air feed side and the permeation side. So how fast are the ions and electrons moving through the material? So there's a couple things to keep in mind with this. How it's fabricated plays into how it performs. Now, looking at the atomic scale, because we're getting really small now, the way this works is these materials are typically made of a perovskite structure. So perovskite, you see this nice little picture. If I look at the cubic structure, the placement of atoms on that, you have A sites and B sites. The big thing to take away is that the A sites and B sites labeled in the picture are what conducts those electrons moving from the permeation side to the feed side. So they basically add the electronic conductivity in the mixed conductivity of the material. Now the other point is these vacancies. These vacancies then occur at high temperatures, which allow it to be highly catalytic towards oxygen reduction, meaning that it allows oxygen to permeate through. So the big thing to take away is, based on the structure, this atomic structure, we can tailor material science to have a combustion application. So you're getting the best of both worlds here. Now, in our lab, we have a very simple setup for how these materials and how the different conditions are investigated. One, we synthesize new powders or used powders that are actually on the market, and then we press them into these little tiny discs that you see that are a little bit smaller than a pen. And they're sintered at very high temperatures, around 1200 degrees Celsius. So I know high is a relative term sometimes. But you can see, if we look at it very, very small, it's a dense structure on the inside as well as the surface. Well, this is shows the surface. But the point is that with a porous cell, you have some mass diffusivity of nitrogen moving through. Nitrogen moving through, the novelty of the membrane doesn't make any sense. Because if you have nitrogen in your system, it's very hard to separate from CO2 at that point. So these membranes are really dense. And what happens is that we seal them up to these quartz tubing here with a high temperature sealant, and then we flush a variety of different gases, helium, CO2, methane, to basically create that partial pressure difference, that chemical gradient across the membrane. And then we characterize the exhaust using a gas chromatograph. So this is typically what a typical research publication result looks like. You have different gases, in this case helium and methane. You have a variety of different flow rates, and you have nitrogen permeable flux that's characterized by the experimental setup that I showed before. So if we initially look at it, we say, okay, sweeping gas flow rate, which is how much is on the permeation side, how much gas, how fast it's flowing. But then you see the increase of that, and you see that methane and helium are typically different. Now, if we go back to the reason why, and this is kind of important, we start laying on for where research investigation is compared to where we are in implementing this technology. A lot of people use helium. Now, there's a substantial difference between helium and methane, and that's because as oxygen permeates through that methane, as it's moving through, it reacts immediately with the methane to produce the byproduct of CO2 and H2O. And because of that, there's low concentration of oxygen. If we have helium, it's inert meaning it's not going to react. And because of that, you're going to have some oxygen hanging out. And there's not much motivation to keep it moving through. That's why we see a difference. The other reason why is at higher flow rates, the difference in the proportions between how much helium or how much of the sweeping gas compared to how much oxygen is disproportionate, more and more and more. And because of that, you have a difference in partial pressure again. So the big thing I want you to take away from this is difference in gases makes a difference in performance. And then we started looking at other differences too. So one of the things we started looking at was LSCF, which you don't have to really know what that is, but the big thing to take away is it's a common material, perovskite material, that you can purchase off the counter. And then we synthesized the new material. And as you can see from both of these presentations, both these graphs, you can see a major difference in performance. Now, relative to the performance, the bigger thing to take away from this is, well, common materials compared to what you're making from brand new scratch is substantially better. The reason because of that is because things that are available on the market are not great. They're not the best yet. When you start thinking about the performance of these things. So the other thing too is that when we characterize how methane is combusted, we look at how much CO2 is within an exhaust stream. So at higher flow rates, again, that ratio between how much fuel is introduced compared to how much oxygen is permeated through is substantially greater for the higher performing cell. And that's the reason why, is because it's permeating more oxygen. And at lower flow rates, that ratio is almost equal. And because of that, that's kind of where you want to operate. You want to convert all that fuel to get a high combustion and a high heat generation from that reaction. The other thing to keep in mind is looking at different catalysts. So not only if you have limitations based on your structure, you can also modify the catalyst in the outer layers to actually improve that surface exchange property. And that's what you can see here. You can see that the surface exchange is improving. You can also see it's improving with temperature. And that's because of the properties of the material and how many vacancy sites are occupying the entire cell. So catalyst enhances it, gases enhances it, and types of material enhances it. So we're looking at these certain factors that really influence and improve the performance of the entire cell. And if we start looking at the overall structure of these things, well, that's when we start getting a little interested. Because as you can see, if I had a really long tube when I'm implementing this technology, I have methane down here, and then I'm looking at CO2 really far downstream. Heat can be collected either through the moving gas or it can be collected through the membrane itself. But we look at this overall picture and identify those parameters so that we can start thinking about how to implement this technology. And that's when we start getting to the projects. So we look at a variety of different projects, and one of the major concerns that we look at is downstream. You can validate a technology sometimes by its weakest point. And its weakest point is at high exposure to CO2. For anybody who works with metals and exposure to CO2, there is some degradation over long periods of time, especially at high temperature. So what happens is we started looking at how this material, and so you see the same stuff we already saw before, how it reacts in the long-term conditions of CO2 exposure. And you can clearly see there's a major difference. The reason why this is occurring is because of the material properties of the cell. At high temperatures, the reaction's a little bit easier. It has the energy required to make a reaction. But at the same time, carbon, or CO2, is building more and more on that perovskite structure, degrading it and actually distorting the entire structure. And the way you characterize these things is you like to look at the performance. You like to look at the total conductivity. You like to look at the permeation. You like to look at the atomic structure. You like to look at the morphology of these things. As you see in these images here, there's a difference. So we can't validate that weakest point, that implementation net, without dealing with this issue. And that's where Project 2 comes into play. We adopted something called dual-phase OTMs. Dual-phase OTMs is dealing with composite materials by adding a stable material to the already perovskite structure. We're not modifying the atomic structure, but we're modifying the composition of the OTM to last for a longer period of time with the addition of a stable material. So the idea is this, is that here upstream you have methane. You have a combination of materials, and it's something that's CO2 tolerant, this is in blue, but it's also ionically conductive, meaning that it can still permeate oxygen ions. So oxygen ions have multiple pathways. But the interesting thing is electron pathways are limited by how many of material A, of the perovskite structure that you have. So that's the reason why you have limitations when you're looking at upstream methane. But downstream, that's where the benefit of these dual-phase compositions comes into play. Because what's happening is, even if the material is modified, so if we go back to this original slide, even if the material is modified, you still have these other diamond vertices structures in which electrons can move through based on the properties of that other site. So that means you still have electron pathways and you still have oxygen ion pathways. So you still maintain stability and you maintain performance by having this inclusion of this additive material to it. And again, similarly to CO2 poisoning, we're looking at the total conductivity up and downstream. We're looking at the atomic structure, if there's any influence between these materials, as well as the morphology and the oxygen flux. But it's not enough. A lot of times when we're dealing with composite materials or even fuel cell technology, what you know, there's interfaces between material A and material B. And a lot of times when you talk about diffusion, you want to know how is that affecting the diffusion process with this additive material or this interface. So in collaboration with Tohoku University located in Sendai, Japan, we're working on a molecular dynamic simulation model that takes the dual phase concept and applies it to an MDS simulation in which we can calculate the diffusion. Now there's also other factors to keep in mind. There's grain boundaries that you see here, there's different conductivities of each material, there's distribution of the material, and we're looking at all these scenarios. But if you start thinking about what that means that we can start modifying compositions numerically without actually touching it with a powder, which reduces cost, which potentially reduces time, and also provides an accurate estimation of, is this going to work? The last project is something that I've been faced with actually the entire time I've had a PhD. Every time I talk to somebody, I might explain the chemistry to them, I can explain the benefits to them, but they always want to know, how big is it going to be? How big? How much is it going to cost? How big is it going to be? And there's not an accurate experimental estimation for how big these things are going to be. Experimental levels, based on the experimental setup that you saw, is very simple. It's a disk, there's some gas over it, and that's about it. It's not converting all the methane unless you have very low flow rates, which we saw with CO2 selectivity. But at the same time, there needs to be an estimation or some comparison. So I started thinking about this issue, and what we started doing is we said, well, if we look at the overall picture and we take snapshots, how does that material perform? And if I have a better picture of how the membrane performs under different snapshots as it moves downstream, well, then I can get an average flux, or I can get an average performance. And then from that average performance, I can get an average size. So what this idea essentially is essentially trying to establish a method in which people who are developing new materials or modeling new materials, and how are they going to implement it, and how well does it perform in an oxy-fuel combustion environment? Because again, this idea is novel in the sense that nothing in terms of this application for natural gas combustion has been implemented. There's no method for evaluating. So how do we do that? Well, we need to start looking at the overall picture and the overall performance. But then we start thinking about outcomes. And being a student here, having the lab at COE, one of the biggest questions that I'm always faced with is, okay, well, how do you do the application? Where's the connection between the experimental work and the application? Because a lot of times, sometimes people can argue that the application is influencing academic research, and then some people can say academic research is influencing the application. What is it? Well, if we look at the outcomes, if we look at the dual phase, what essentially it's doing is providing a high-performing, stable OTM that can be implemented in all atmospheres. In other words, we're not looking at the context of how the material performs or what condition it performs under, but we're thinking about the end application that basically modifies how we conduct those experiments, so that not only can people in our field understand, but maybe people who are passionate about implementing technology that can mitigate carbon emissions may also understand too. We also look at the molecular dynamic simulations of OTMs and developing new materials. Not everyone's a material scientist, but they want high diffusivity. They want high oxygen permeating through that. And the big thing is that it's estimating oxygen permeation of any materials that are fabricated. The other thing that's interesting about this project is its international collaboration. So I had the pleasure of working in Japan at Tohoku University 2 years ago. And the cool thing about it is people's perspective on climate change technology of different countries. Some people it's more immediate, while other people in other countries might be listening to so many voices they don't know what to do. But working together and getting that perspective allows you to basically utilize all resources to get the best outcome, so that you're really benefiting the world and not just a certain community. And I really got a lot out of that project. The last thing is exploiting OTM experimental results, or extrapolating OTM experimental results to the point where we're getting an estimation or a method for evaluating these things. There's no method that's currently available that compares conditions as well as material that are available for OTMs. And that's an issue. So we're trying to combat this by saying, if I have a simple setup, here's how it's going to perform in the end. And that goes back into playing with application and experimentation. But perhaps the biggest outcome is a solution today for a greener tomorrow. A lot of times this project not only touches around experimental work, but also touches around policy. It also touches around how we actually function in society, whether we're using a lot of electronics or we're using a lot of power sources that require them to produce more and more emissions. And it breaks down to the experimental of what motivates us to get out of bed and actually start researching in the morning. So those are things to keep in mind when we're talking about OGMs as well as the code lab. So thanks very much.
We'll take questions if I could jump in with one of my own. It's kind of sequestration ends up being one of those things that an issue that everybody's focused on, and it always seems that there's three things that always kind of puts it a little further away. The capital costs that for the actual implementation of the solution, the first cost, or the running O&M cost that it takes throughout the course of time while doing the sequestration, or the last one, which is the one that's the intangible, which is the political will and the will for policymakers to actually make it happen. Comparing your approach and what you see, how does it sort of set in that backdrop?
That's a good question. So I'm going to reference a slide that I have. That's good. So this technology of ion transport membranes is already implemented for one purpose, and that's for hydrogen production. And that's done by Praxair, who I've actually done by Max Christie at Praxair, and I've had conversations about this. The reason why is because hydrogen is value to it. The CO2? Not really. CO2 is a byproduct of combustion. You breathe it out. But the idea more or less is this technology cost effective to build? Now, one of the benefits of this is it can be retrofitted in current plant designs. Well, some things you think about have to rebuild the entire plant from scratch, so there's a benefit there. And then you start thinking about, okay, well, operating benefits. Long-term stability, meaning that's why we're dealing with CO2 poisoning. Is it going to last for a long period of time? Ceramic materials are already implemented for that purpose, even for hydrogen production. But the other thing to keep in mind too is at high temperatures, is it going to crack in any way? So we also deal with that on a research level. But operating at a long cost, there's no need for external circuitry, and you have a simplified model in which only requires initial heat that can be sustained from the combustion reaction inside. So it is possible, but there's other things that need to be investigated for.
So there's not a lot of sacrifice for loss in terms of the energy to actually make the solution occur, right? From the power plant itself.
Yeah, so essentially, if I wanted to implement an oxy-fuel combustion process, and I said, okay, I just have to build a whole other building to essentially house all this stuff, but I could be implemented back into my original system by feeding the X turbine here or this compressor here. So yeah, it's cost effective in certain models, but in another model, it's like, well, it's not if they do X, Y, and Z. Depends on the need.
I take questions from anybody out there.
Yeah.
You know, you're talking about methane, right?
Yep.
And pipeline quality natural gas throughout the United States is not necessarily even close to being the same. Or at least has cleaner gases like that in Texas. What about like heavies in natural gas and things like that?
Pardon? What else?
Heavies, you know, or hydrogen sulfide? Or
Yeah, that's a great question. So
you consider that in this?
we have hydrogen sulfide is interesting because we also did an application for biogas technology, and that was dealing with not this immediately, but fuel cells. And one of the things that, and this is when I'm doing my master's, I investigated, okay, can this run under hydrogen sulfide? And in certain cases it can, depending on the temperature. But the bigger thing that I asked is building the system. And a lot of times, I think in New York State, they require scrubbers for certain areas of sulfur before they enter some reactor. So there is ways to filtrate that out before it's introduced into the membrane. But in other cases,
Yeah, but it's successfully to do so is not, you know, I mean, theoretically scrubbing it works well, but oftentimes in a real application, it doesn't quite work as well as planned. And
nothing's
I'm sure to
ideal.
make sure, right, but I'm just making sure you consider that in your catalyst.
That's a great question. We go back to the CO2 poisoning slide. The reason why it reacts, I don't want to get too much into the nitty-gritty because people get lost in chemistry sometimes, but you have a carbon approach. With hydrogen sulfide, that's less likely to occur based on what materials you still have A and B site. We have a little bit, but we don't see a tremendous amount of sulfur poisoning when it comes into that way. And from other reported literature with this kind of material, they don't really see the same thing. It's basically that carbon information on the A site and its reactability with the CO2. So, yeah, from what I've seen in the literature,
Didn't want to see you get screwed along the line.
that's okay. Yeah, well,
So you discussed trying to mitigate the problem of surface, like control of the surface flow versus like the gradient of how you would permeate oxygen through the material.
Mhm.
My question is how much control do you have over that gradient? Like when you that chemical gradient that you use, like
controlling what?
can you, like on the molecular structure, are you able to edit that? Like how do you change that gradient, and like what is that gradient?
Yeah, so it depends on a couple things. The gradient is driven by the partial pressure, so how much oxygen you have on both sides. So in certain application cases, you can have pressure on one side being a lot higher, which means the oxygen concentration might be higher on one side compared to the other, driving it home. In terms of material science, you can tailor how many vacancy sites or how much disorder is caused when you have a collection of these cubes all in a row. So that mainly depends on, and we talked about this yesterday with dopant strategies. So you might add a lot of material A or A site into one structure, which might cause some disorder as it's heated up. And the approach that people do with that now is they do a dopant strategy of, okay, I'm going to add the proportion between B site and A site 1 to 9 and 2 to 8. So they might be varying that enough so that a lot of vacancies are created. But at the same time, you have to worry about membrane stability and fabrication when you're heating up. So that's where a lot of research has been done around 15 years ago. With you're sintering something at high temperature, well, the bonds between them start breaking apart, and so you start seeing these globs. The big thing is you really want a material, when you start talking about making new materials, something that's going to be densified at a relatively low, not like 1500, but 1200, it's relatively low, temperature so that it's dense and it's easy to form really well. So some materials have that challenge based on what you're doping with. Yeah.
Thank you.
Yeah.
So I'm thinking about the scale up. You know,
Okay.
you imagine that these can get to a power plant scale because you're getting, you know, when you're talking about hydrogen production, it's a little bit smaller scale.
Yeah.
I forget what your process is.
Yeah, it's scandium strontium.
So, and that's not, you know, the most common elements, or you're concerned about large scale production. Consider materials.
Yeah, so material integration for like certain purpose gate structures. The reason why I mainly selected this is because we're mainly trying to highlight trends.
Yeah.
And like you have LSCF, which is fairly common, and that's fairly common because the materials are used are pretty readily available, but it's lower performing. So a lot of times, if I'm looking at something like this experimentally, I'm not seeing that great big variation in trend. And if you're modifying stuff on such a small scale, you want to see that. In terms of scaling up, the bigger idea is applying methods and approaches that you can evaluate new materials on that might be more cost effective, so that you may be able to scale on a larger scale. Like for the hydrogen production, I don't think it's a little bit smaller compared to like what people propose for power generation. But again, if you look back when I started talking about surface exchange properties, I mentioned nanomaterials, which is becoming the forefront of a lot of material research. And if you get something that small, it can be mainly depending on how well it's a conductive material.
Yeah, I think you're still not going to get anything with that.
No, it's mainly just highlighting those trends. Yeah. So, yeah, it's not the end. There's not one end-all be-all material that's going to solve all our problems, or is there? So, yeah, but that's a great question.
Is that it for us on any questions for Ryan? All right. One last one.
I just I thought this project is excellent, but I'm just wondering one question: how do you recycle the material? Or
So, from cradle, you're talking about when it's all said and done, how to recycle the materials. So that's an interesting question. There are ways to break down these materials that are simply like metals. For the dope Syria, you could use some acid bath to clean out one and then reuse the dope Syria, which I've done a couple times. Like when we're talking about here. So like there is ways to recycle some of this material. In other cases, bringing it back, I'm not sure about. There are certain safety precautions that would have to be put in place before you implement something like this to actually get rid of it. But being something that's high temperature, I don't know if there's current methods out there for actually disposing of fuel cells, but that is another issue that people are talking about now. That being said, compared to liquid electrolytes that are typically implemented in batteries, it's a lot easier to dispose of something that's in a solid state compared to a liquid state, and it's a lot safer too in certain cases. So, yeah, but that's a great question too.
Thank you.
Yep.
Right. Thank you, Ryan.
Yep. Thanks.
I'll try to manage a couple things at the same time. One, our others, maybe I'll ask for assistance because I think Carrie helped us in the setup. So, thank you, Ryan. Our next speaker is Peter Wilcoxen, and he is a professor of public administration and international affairs at Syracuse University's Maxwell School, Center for Environmental Policy and Administration, and is a SyracuseCoE fellow. Pete's principal area of study is in the effect of environmental and energy policies on economic growth, trade, and the performance of individual industries. Today, he will present results on the potential role of a modest carbon tax could play as part of a tax reform initiative in the United States. The carbon tax analyzed would reduce annual carbon dioxide emissions substantially And the new revenue generated by the tax could be used to offset reduction in the tax on capital income, which would then lead to increased investment in GDP, including a carbon tax and a tax reform package that would end up resulting in the expansion of our economy. Peter, welcome.
So thanks everyone for coming. I was sort of struck, this is kind of a sad event for me because in my earlier life, I thought taxes were about the dullest thing in the world. And I thought the kind of stuff that Ryan was talking about was really interesting, but here I'm going to talk about tax reform. So bear with me because I have followed a path to get here, and I think it's what I'm talking about. I believe in. I think it's important, but it's quite different than where I expected to end up. Okay, so let's see if I can operate this. Okay, so I'm going to talk about some work that I've been doing with a couple colleagues, one from Australia and one from Brookings. The project is housed at Brookings. And we've been doing work on carbon taxes, both in the US and at the international level for quite a while. We have a series of papers on different aspects of carbon taxes, whether they're a good way to cut carbon or whether tradable permits would be better, how they compare to policies implemented in the electric sector alone, which until the new administration came in, the Clean Power Plan looked like the way that we were going to deal with carbon. But today, I'm going to talk about carbon taxes and tax reform. And the motivation for that, of course, is that we're about to launch a tax reform effort in Washington. And so a lot of people who've been worried about climate are hoping that this might create a little tiny window for a carbon tax to be integrated into the package. Just to get things started, carbon tax, if you haven't spent half your career studying this, is a tax on the carbon content in fossil fuels. One of the things that's attractive about it is that it's easy to measure the amount of carbon that's in a fossil fuel and to understand how much CO2 will be released when you combust it. It doesn't require stack monitoring like a lot of other kinds of pollutants. It's one of the reasons that people talk about it as a carbon tax rather than a CO2 tax. But there's a simple chemical conversion between a carbon tax and a CO2 tax based on the atomic structure of CO2. And so what I'm going to be talking about today as an example tax is a tax that would be $15 per ton of CO2, or if it were levied on the fuel itself, it would be about $55 per ton of carbon. All right, and so the point of a carbon tax is to create incentives, and it creates a lot of incentives to reduce carbon emissions in the economy. It turns out that there are 4 things that you can do, and realistically, we're going to have to do all 4 of them. One of them is fuel switching, to move from high carbon fuels to low carbon fuels. And so as many people here probably know, in particular, that means moving away from coal and toward natural gas in terms of fossil fuels. We're moving away from fossil entirely toward nuclear or renewables. That's, in some sense, the politically easiest kind of transition to make because it's upstream. It occurs way far from most of the electorate. You probably did not get up this morning and wonder what your electricity was made out of, right? It just shows up. The second thing that can be done is to use energy more efficiently. Right? So we can, well, the COE, everyone is in the COE. The COE's mission is to get people to use energy more efficiently. So I will not elaborate on that. But that requires buying new devices, essentially. The third thing that can be done is to ask people to use fewer energy services, right? Not to turn on the lights or not to adjust the air conditioner. And that's a bigger political lift. People of a certain age will remember that President Carter asked people to do that and wore a cardigan on TV. And had there been an internet at that time, it would have within seconds have been viral meme, right? He was mocked mercilessly, even before it was easy to mock people mercilessly. Okay? And then the fourth thing is sequestration. It's to capture CO2, either during the combustion process or directly out of the air, and take it out of the biosphere. And so a carbon tax provides, in principle, incentives for all these things. By making fossil fuels more expensive, there's an incentive for people to use lower carbon fuels, to buy less energy and use it more efficiently, to reduce energy consumption, to turn off the lights when they don't need them, and then to pay for really cool inventions which keep the CO2 from getting into the atmosphere in the first place. All right, so how a tax would work is basically straightforward. The tax would be applied, and it gives firms an incentive to eliminate all of the CO2 they can at low cost. So the way that economists talk about this, anybody who emits CO2 has a cost curve for abating emissions. And when a tax goes into place, they immediately have an incentive to avoid the tax by making these low-cost efforts to reduce emissions. So carbon tax at the outset is not intended to eliminate CO2 entirely. It's just intended to eliminate the cheap CO2. Okay? And policymakers have a lot of power in deciding exactly how far up this curve we want to go. With a low tax, you pick off the low-hanging fruit, but then as the tax goes up, you ask people, or you give people an incentive. Ask is probably the wrong word. You give them a financial incentive to do more. Okay. Now, the other thing that I wanted to have up here in this diagram is really the tax reform part. Because a tax, a CO2 tax, is usually not designed to eliminate CO2 entirely, there'll still be a lot of emissions. So if this is original emissions, 100 tons, say, and we eliminate 30 tons, we're still going to have 70 tons of emissions left, and the tax will be applied to all of those tons. So to give you some idea about scale, the Obama administration had was interested in reducing CO2 emissions, U.S. CO2 emissions by 17% relative to 2005. In 2005, we emitted from energy sources about 6 gigatons, 6 billion tons of CO2. And we're basically trying to knock a sixth of that off, which is a good achievement. And that would drop us down to 5 billion metric tons. Now, in terms of revenue, if you had a modest carbon tax, like in the sense of, not quite in the sense of modest proposal, right? Jonathan Swift, but a smallish carbon tax, right? And 5 billion tons of things that are being taxed, you raise a significant amount of revenue. So that's a pretty low carbon tax by the standards of these things, and it would still raise $75 billion a year. And so from my point of view, the idea of talking about this now is being able to dangle $75 billion in front of people in Congress who are thinking about tax reform can be helpful. All right, and just to put things in perspective, that creates effects downstream because the tax on fuels will in large part be passed on to people who buy fuels and eventually combust them. So a $15 ton of CO2 tax would translate into about 13 cents per gallon. It raises natural gas prices somewhat, and it raises electricity prices 0 to 1.6%. And the 0 to 1.6% is not because of deep uncertainty, it's because it really depends on the fuel mix of the area where someone lives. So just because it's politically important and also interesting, if you imposed a $15 a ton carbon tax now, and states didn't change the fuel mix of their electric power, and all of the costs were passed on to ratepayers, what you'd end up seeing is a set of changes in electricity prices that look like this. So the light-colored regions have 0 to 0.6 cents increase in electricity prices. So So if you live in this area, you're paying around 14 cents, 13, 14 cents. National average is lower than that nonsense. So these light blue areas have low increases in electricity, and possibly not coincidentally, some of the places that are most enthusiastic about climate policies are ones that have the least at stake in terms of this. Okay, now, the reason that we have the least at stake in New York State and California, I'm used to teaching classes, it's so tempting to ask you why. But that's rude. So the reason why, though, is because those states have already, for the most part, California, New York, some of the other states, have already done their job, right? We have high electricity prices because, relative to these other states, we don't burn very much coal. We have cleaner electricity already. One big difference, of course, is this area, which is just full of hydropower, of course. So they have issues with salmon, but they don't have issues with carbon. Someone called me up from a newspaper in Seattle one time and said, carbon tax has been proposed here. How will it affect people in Seattle? And I said, well, it's not going to affect you much at all in terms of your electricity bill because you don't burn any carbon. Now, the rest of the country, of course, is not like that. And so you can see some states that have lots of coal. And as everyone is probably intensely aware, each of those states have 2 senators, which is the same number as the other states. So this is a pretty complicated political process. And it isn't mysterious to people who live in these states, what they burn for electricity. Okay, now, before I get into the details of the research that we actually did, I want to tell you about what for economists is about as close as close to an experiment as we ever get. Okay, and that's when somebody conducts a thing which accidentally looks like a natural experiment. So a question that you might wonder is, would a carbon tax work? And if you haven't spent a lot of time drinking economist Kool-Aid, you probably think, well, people don't really pay that much attention to energy prices. They wouldn't do very much in response. But we actually had an experiment conducted courtesy of OPEC in the 70s and 80s. And here is a little information about what happened. So in this curve, here in this green line is actual US energy consumption, and probably everyone in this room will be offended to know that it's in quadrillion BTUs, right, rather than exajoules. But that's how US energy is measured at a large scale. So this green line is actual energy consumption, and then a few of you have seen this graph before, and I apologize for inflicting it, but I really like it. Okay, if you take Microsoft Excel, which is the lowest grade statistical tool you will ever see in your life, and you fit an exponential growth curve to this, you get a thing with an R squared of 0.98. And you find out that the estimated growth rate is 3.4, and the standard error is 0.0 something, right? You get the best fit you've ever seen in an analysis that wasn't faked, okay? And as, again, people of a certain age or students of the electric sector know, people back in the era, this is up into the mid-70s, ran these regressions, and they knew what energy consumption did. It grew at 3.4% a year every year. It just grew because they had these statistical models which fit beautifully. But then in 1973, again in 1979, there were big increases in oil prices, and those fed through to increases in other energy prices. And what actually happened was that for about 15 years, US energy consumption was essentially flat. It bopped up and down a little, but it was basically flat. So if somebody says the US could never stabilize energy consumption in the modern world, that is wrong. We actually did it. Energy consumption eventually grew. Now this is without adjusting for population growth. This is total energy consumption in an economy that is growing with a population that's growing. It's basically flat through here. And it's trickled up a little. We now use about 100 quads. And this is what you would have thought we'd be doing today if energy prices hasn't changed. We'd be using twice as much energy. Okay? Energy prices matter. Okay? They matter a lot. And the reason that everything was so smooth before 1973 is that for decades, energy prices had been both low and stable. And so nobody paid any attention to them. But once they got into people's, people focused on them, once they got high enough to matter, a lot of things started happening. Now, lest you think that what happened was we ended up in a recession which lasted for decades, this is a graph that shows what happened to energy and what happened to GDP. And unfortunately, I didn't color code it very well, but this line here, this dashed line, matches up with the previous green line. That's actual energy consumption in quads. And this is US GDP, right? So real US GDP after adjusting for inflation. So to be sure, there are ups and downs, right? It was kind of a hassle dealing with the oil crises initially. So there's recessions along the way here. But GDP growth was not killed off. Where a lot of people in the political, frankly, will tell you energy consumption and economic growth are inextricably linked. If we cut energy consumption, we're going to have lower economic growth. So they're telling you that this would happen. Okay? No. Okay. And the reason why is everybody who's here, right? I mean, there's legions of people who are willing to figure out how to not use so much energy once there's a financial incentive to do it. Okay, so now I'm going to turn to talking a little bit about what would happen if we tried to use the price mechanism deliberately rather than having it inflicted on us by political adversaries, right, overseas. So I'm going to talk about some work we did analyzing a relatively small carbon tax, one that starts at $15 a ton and rises faster than inflation at 4% a year. And there are some important economic reasons that it needs to rise faster than the inflation rate. So that is standard in thinking about carbon taxes. And what we were interested in doing is understanding what the impacts of that would be on a bunch of things, like would it work? Would it drive down emissions? What does it do to revenue? What does it do to the economy as a whole? And so on. And then for our paper, the main thing that we were really interested in was what should be done with the revenue. So the government, if it levies a carbon tax, is going to be collecting possibly a large amount of revenue, and it has a lot of options. So one option is that it can give it out to people. Okay, but that's not the only thing it can do. It could use it to cut capital taxes. So if you haven't been following the discussion in Washington, right, that's one of the things that is really on the table, is cutting capital taxes. It could be used to cut labor taxes, payroll taxes, or it could be used to reduce the federal deficit or subsidize things, many possible uses. So to analyze this, my colleagues and I use what's known as a computational general equilibrium model of the world economy. So what we do is divide the economy, the world economy, up into 9 regions. Some are matched to countries, some are matched to broader regions, OPEC, for example. And then each of these countries we subdivide into 12 sectors, 12 producing sectors, as well as a household and a government entity. And then we use economic data to fit statistical models of the behavior of each of these industries, as well as the households and investors and governments within each of these economies. So in a sense, what we do for each of those sectors is we map out and build statistical models of their demands and supplies for each of the 12 goods produced in the economy. And that allows us to track the effects of a carbon tax in great detail. So if a carbon tax gets levied, one thing it does is it raises coal prices downstream. So it's going to have an impact on the coal sector. But then coal prices are going to cause, in the power sector, some shifting to natural gas, okay, which of course has happened in spades already because natural gas prices have been low due to fracking. So we're going to pick up that connection. natural gas prices, well, gas prices impact the use of natural gas. That downstream affects electricity prices, which is how most people will experience the policy. That in turn affects durable goods prices, things that are produced in the economy, and those affect international trade. So the model that we have, because it has these connections between sectors and between countries, allows us to track those things. So for this study, we set up 7 different scenarios to run through the model. And the first one is, so the model, so if you do any kind of numerical analysis, this is just a really large system of partial differential equations, basically, that we solve subject to a bunch of inputs, forcing variables, and boundary conditions. So we start with a set of assumptions about population growth, technology, tax policy, and so on, that we think of as business as usual. And then in the paper that I'm referring to, we ran 6 other simulations looking for scenarios, looking at a mix of things that could be done with tax reform. So one that I'm going to talk about today is a carbon tax paired with a lump sum rebate. So lump sum rebate is giving the money back to households. Okay, it's your policy, Kyle. We also looked at what would happen if you used a carbon tax to reduce the deficit. And then for comparison, we looked at what happens if you use a labor or capital tax increase to reduce the deficit. We looked at what happens if you use a carbon tax to reduce labor taxes. And then the other thing that I have highlighted here is the main thing that I'm going to use to compare to the base carbon tax is what happens if you use the carbon tax to cut capital taxes. So I'm going to focus on the first and last of these policy scenarios, and the only difference is what's done with the revenue. So just to visualize it, this is what the carbon tax looks over time as it goes into the model. In the initial year, $10 per ton, and then it rises to about $40 25 years out. Okay. And then this is the base is down here. It has no carbon tax, but all these other scenarios have the same tax rate.
Good question.
Yeah.
You said 4% real.
Yes.
So is that 4% plus inflation?
It's 4% above inflation.
So there's an assumed inflation.
Yes, we have a built-in inflation rate, and the 4% is on top of that. That's right. Since you asked about this, one of my colleagues is a monetary economist, and so he spent a lot of time building in at the beginning years of this scenario negative interest rates, right, and negative inflation rates in some of these countries, which is going on because there have been periods of deflation, which is a pain in the neck, really, right? Both for the world, right, and for us. Okay, so as many of you know, who have either heard conversations about carbon taxes before or read about it in the media, in the U.S., this is a big deal for the coal sector and not such a big deal for everyone else. So this shows what happens in the U.S. if we adopt this carbon tax I showed a few minutes ago in year 15. So it's kind of in the middle of this period. There are 3 different taxes shown in this diagram. They're goods along the bottom here, and this is the coal sector. There are 3 colors because there's a distinction between the producer price, which doesn't include the tax, the purchaser price, which does include the tax, and then a price after adjusting for the fact that some of these things are imported and their exchange rate changes as well. But basically, the story here is that this tax causes the price of coal to go up by about 70% in year 15 of the simulation. These are the other energy sectors. I should have mentioned that the sectors at the left, the first few sectors are all energy sectors: electric power, gas deliveries, refining. They go up. Crude oil and raw natural gas go up as well because they're subject to the carbon tax. These sectors all buy these things as inputs, so they're prices go up, but not as much. Now, the reason I put this up here is, and I kind of apologize for it, because if I had a graph, it would be the dullest thing ever, okay? The reason I put it up there, though, is because I want you to see these things out here, right? They're hardly visible. This is a story about what happens to the energy sector. Everybody else downstream, this is not going to cause their cost to skyrocket. Energy is a small part of most of these sectors' costs, except for very narrowly defined sectors. And as a result, their costs don't go up very much. So the main action of the policy occurs in the energy sector. That's also true in terms of sales of goods. This is what happens to quantities and percentage changes from the baseline. So the primary fossil fuels go down by coal about 22% relative to baseline, the other fuels less. And then over here is the services sector, right? If you can see that little blip, most of us, this is good, right? There's a slight increase in output of the service sector. Okay, so that gives you some idea of what the tax does to the economy. Now, does it work? And the answer is yes. This is what happens to carbon dioxide emissions, U.S. total carbon dioxide emissions from energy consumption. So there's an initial drop. These are in billions of metric tons or gigatons. So there's an initial drop when the $15 tax kicks in. And then as the tax increases over time, the drop becomes bigger relative to baseline, right? So these are all relative to baseline, decreases relative to baseline. So baseline emissions are going up, and the carbon tax is keeping them from going up as fast. We're 20% below baseline in year 2025 with this, or by 25 years out. And this has reduced cumulative emissions, which for climate is the measure to care about, not annual emissions, by 20 billion metric tons. Now, in terms of tax policy, it raises a lot of money. So this particular tax, when you look at the amount of emissions that are actually present after the tax kicks in, raises more than $75 billion because it doesn't cut emissions quite as much as the Obama administration goal. We end up with $83 billion initially, rising to $200 billion 25 years out.
That's
Annual, that's annual, right? So a number like that is enough to get attention in Washington. This is enough to get your phone call answered, right? But now, Sherry might correct me on this if I got the orders wrong. But we ran this out to year 25. If you look at the really long run picture, our carbon taxes are not a good source of revenue in the really long run, because eventually what happens is the tax gets high enough that emissions drop off, and then the tax rate erodes faster than the tax itself rises and emissions go away. So carbon taxes, if all goes well, are a temporary policy in that sense. Okay, now the important thing about what we found in this paper is that what happens to the economy as a result of this. So it works to cut emissions. What happens in the economy depends very heavily on what you do with the revenue. And so as I mentioned, we looked at a bunch of different revenue policies, and one of them, which is kind of the reference case, is to give the money out to households via lump sum rebate, right? Just to cut people checks each year. That turns out to raise GDP a little bit initially, because people will go out and spend that money. But in terms of raising GDP, giving a capital tax cut actually has a much bigger impact, right? It raises GDP much more because capital is taxed relatively heavily compared to other things in the economy, and capital taxes are a disincentive to investment. So when we use all of this carbon tax revenue, we're able to cut capital taxes enough that it creates more investment. And so this is a graph just showing aggregate U.S. investment relative to GDP. And most of the policies that we looked at, the carbon taxes with different kinds of revenue uses, have not very much effect on investment, a small negative effect. But this capital tax reduction has a big effect, right? We cut capital taxes and that stimulates more investment. By stimulating more investment, we actually get an increase in employment, okay? An increase in employment. So whenever you open a newspaper or something, you'll see people saying you can't tax energy because it's going to throw people out of work. Well, it depends on what you do with the money. So down here, this green line is what happens to overall employment if you give money out as a lump sum rebate to people. So it's not a very large change, but it isn't helpful, right? The sectors that produce energy now are going to get smaller. People who work in those sectors are going to be unemployed for a while. It's going to take a period of time before they get employed elsewhere in the economy. If you do something that stimulates the economy with the revenue, that kicks off an investment boom, you can actually increase employment, okay? So the thing that I want you to take away from this, you don't have to believe these numbers per se, but the thing I want you to remember is that the employment impacts at an aggregate level of a carbon tax are not baked in, right? It depends a lot on what you do with the money. Okay, this is just zooming in on where the employment ends up, and it ends up in durable goods and services, but we don't have to go into great detail on that. By increasing employment, draw real wages in the economy, which is a good thing as well. And a thing that is really important to remember about all this is that these changes turn out to be kind of small compared to the size of the economy itself. So what this graph shows is GDP growth in the baseline. It's that green line. There's a green line there. That's GDP growth in the baseline. This lump sum tax policy that I was talking about is a dashed line. And frankly, unless you guys have better eyes than me, you cannot see the difference. Okay, and the point is that the carbon tax has not crashed the economy. Right, but like a recession is, that curve going down. It's not going down, okay? It's going up a tiny bit more slowly. But the change in growth is very small compared to the overall rate of growth in the US, and you can't even see the difference. If you stimulate the economy with this investment policy, you can actually see a slight difference, which is slightly higher growth, okay? So the effect is small compared to annual growth. And a really good way to see how small it is to zoom in on year 24, right out here near the end. Okay, so, oops. If you zoom in on year 24, the green line, what I've drawn here, this horizontal line, is the amount of GDP we expect to have 24 years in the future. And then this red line shows that if we adopt the carbon tax and we use lump sum recycling, we don't get year 24's GDP in January 1st. It doesn't, our GDP level doesn't rise to that until February 1st. So it delays the level of GDP by about a month. If you use a capital tax reduction instead, you end up accelerating growth slightly, so you get future GDP slightly earlier. Question?
Yeah, I was just wondering, does this model like incorporate like predictions as far as if industries start shifting to more renewables, then you'd have less carbon and so like therefore like less revenue for all that?
Yes, all of that's taken into the account. So we have so the reason for having a model that has multiple sectors is because we can pick up those kinds of effects. What I thought you might ask, and so people might wonder about, is this model does not have any feedbacks from the climate back to the economy. So there's no feedback in here that says, well, if we do this, we end up with slightly different warming and slightly different consequences. That is not included. Good luck with that. Yeah, I know. Okay, so quick summary. What policies are needed to deal with climate? And the answer is we have to make fossil fuel more expensive. We could do that with carbon taxes or cap and trade policy. And that's essential to make the investments, all the things that we talked about that you can do to reduce carbon, someone has to spend money on. And carbon tax can make it profitable to do that. The second thing is that historical evidence is optimistic. We've had events that had huge effects on energy consumption and emissions, and we know that those things do not crash the economy, especially if they're managed well. And then the thing that I wanted to leave you with at the end is in terms of how much they cost. Okay, so Ryan's not at the point where he can tell you how much a power plant will cost built out of these cool materials. But the answer is that this work, but not just my work, everybody who works on this really finds that the cost of these policies is surprisingly little compared to the size of the economy. Now, when you go to talk to people from Congress, right, surprisingly little relative to the US economy is still a very large price tag, right? Turning over the US generating stock and making it carbon free is got a price tag, if you could do it, an overnight cost of $1 to $2 trillion with a T, right? It's a lot of money, but the economy is large, it's growing, and if you phase in a policy like this, you don't have to strand everyone's capital by allowing them to build things that you later put a tax policy in place on and render them unprofitable. And finally, the outcome is even better if you're smart about how to use the revenue. Okay, so I think I have used up my time, but I have also used up my slides. So.
Characterization of the political will right now, which seems to be probably a little more in jeopardy, even if you could rebrand it instead of carbon tax, even carbon tax reform. So what are your feelings regarding just the political will at the moment?
Well, there's a window, right? There's a window of opportunity. Like there are times when you can talk to people in Washington about this and times when you can't. And tax reform is a window. And it's an important window because you would be hard pressed if you go out and scour the Wall Street Journal or pick whatever periodical you'd like. You'd be hard pressed to find an economist anywhere on the political spectrum who is against a carbon tax as part of a tax reform policy, right? It basically has lots of things to commend it, right? It reduces a problem rather than taxes on labor and capital, which reduce the thing that we'd actually want people to do. We want you to go to work, but we tax you on that. So that's kind of disincentive to go to work. Here, we don't want people to emit carbon. We could tax it. That gives them an incentive not to do it, but it still raises revenue. And so the more serious that Congress is about tax reform, the greater the chance that this could come about. But one small glimmer of hope is that people on, so this has been a politically charged issue, but there are people on the Republican side of the aisle who are now talking seriously about this. And if you want to hear some of them talk about it, there's going to be a talk tomorrow, the panel discussion tomorrow night at the law school that features two former Republican congressmen who are going to be talking about the prospects of carbon taxes and other market-based policies. And like, to be clear, right, they are in favor of it, which is a sea change from the way things have been sometimes in the past. So there'll be several people there, including me, and I'm hoping to hear really optimistic things tomorrow. 6 o'clock over in Dunedin. But I've been doing this for longer than I really want to talk about now. And it's slow. States have taken steps in this direction, but it's going to be slow. And so there's a window. We have to be hopeful about this because the problem is not going away, but it's not a done deal.
In terms of implementing a carbon tax, how much is reduced in the overall scale of our commitment to climate talks relative to?
Well, so the short answer to that is it depends on how high you set the tax. The long answer to that is that the U.S. obligation under the Paris Accords would have been met almost entirely by the Clean Power Plan, which is a regulatory policy for the electric sector, and CAFE and ratcheted up CAFE standards. So the Obama administration basically made commitments at Paris that could be carried out without a carbon tax. But I think the reason that these people from the congressional representatives who are going to be here tomorrow are enthusiastic about this is that giving people incentives with a tax policy is almost always a lot better and cheaper as a way to get things done than walking into their factory or power plant and telling them that they have to install particular kinds of capital. So we could have gotten there with the Clean Power Plan. A carbon tax would be a cheaper way to do it, to get to the same place.
A couple questions. Is it a fair and equitable tax to have that flat rate for, somebody in West Virginia or South Dakota versus someone in Washington and New York? And then off of that, with the military being a large consumer of energy, how would this affect them?
Well, so in terms of equity, that's a great question, and I'm going to actually split it into two questions. So one question that people worry about is, what about low-income people that use a lot of energy, right? And so in economic jargon, the question is, how regressive would an energy tax like this be, right? How much extra does it burden people with low income relative to their income? And the answer to that is that a carbon tax is a little bit regressive, but it's basically easy, if you want, as a policymaker, to mitigate that by making small changes in the income tax code. So carbon tax does not have to be regressive in terms of low income. The second part of your question is, what do you do about the fact that some people's income, in particular regions of the country especially, is tied to the sectors that will get smaller? Okay, and so I think I heard that there has recently been a statement circulating about how not to deal with that. I think it was someone named Clinton who has a recent book out that says, do not stand at an open mic and say, we're going to close a lot of coal mines and put coal miners out of work, right? That was actually not a really good way of talking about this issue, right? It is true that to deal with climate, coal production is going to have to be reduced, or we're going to have to use post-combustion sequestration, which unfortunately I think your technique does not apply to. Cool. If you make syngas out of it.
You could actually. So that's what current models are implementing with TMC for coal combustion. So it's possible, but you still
you have to gasify it.
Yeah, so it's a different technique, but yeah, it's possible.
But to come back to your question, so this is a place I think the reason that we still have this problem, and the reason that we're even having this conversation, is because Congress in the past has done a spectacularly bad job of dealing with industries that decline because of policy reasons. So my evidence for this is we now are worried about people in West Virginia and other coal mining areas, and there's a lot of discussion about the way of life of people and how carbon policies destroy that. But some of you have probably heard, or maybe remember yourself, a generation ago when I was young, nobody was going around saying that, nobody in West Virginia was going around saying, I really hope my children grow up to be coal miners, right? They wanted their kids to get out of coal mines, right?
I think you misinterpreted my question. I was just asking about the difference in energy costs. I wasn't asking about
difference in energy costs. Okay, well, the big cost.
Just before you went on.
Yeah, all right. So the big political problem is, what do you do about retraining people who have worked in a career for their whole professional life, and that career is going downhill. In terms of energy cost, I think the first answer is that we can tweak the tax system to deal with it. Okay. Any other questions I can misinterpret?
And probably no, because I thought you use the number that energy price strongly affecting consumption. So I'm still a little bit confused because I noticed that the energy is actually the power of the economics. So if the economics grows moderately, so how that's going to be strongly affecting the consumption? I mean, what the evidence shows this kind of energy prices, because I thought energy is kind of the inelastic good. So
well, so the question is energy inelastic for buyers, and do they not pay much attention? So that's economic terminology for people not paying much attention to prices. And the answer to that is twofold. So in the short term, people are pretty inelastic. So my sensitivity to gas prices is very low because I have a car which has a particular fuel efficiency. And while I'm driving that car and I have to commute back and forth, I'm not very sensitive to gas prices, kind of. Now, it turns out that my wife and she drives an electric car. And so if gas prices really go up, she has a shorter commute than me. And so I would switch, right? So, but other people would do the same thing, right? So, you know, there'd be any household that has multiple vehicles with different fuel efficiencies. If fuel prices go up, they can switch, and that reduces their energy consumption. Over longer periods of time, people can buy more efficient appliances and more efficient vehicles and reduce their consumption that way.
okay.
Kyle.
My understanding was that a lot of larger proportion, and I thought originally of people's individual carbon footprint is embedded in the products they buy, as opposed to direct energy consumption. Is that?
Well, it's true. So it's absolutely true that most people don't burn. A lot of people burn very little fuel at home, right? So like my carbon footprint is driven much more by the imputed carbon that's burned on my behalf for electricity generation than my actual furnace, right? And so that's also true for some of the goods I buy. The flip side of that, though, is that 70% of U.S. carbon emissions come from electric power generation and transportation fuels. So.
Yeah, I guess I was just curious in the response in the embedded piece where you showed that hardly any price increase would happen in durable goods and consumer products or what have you. So I didn't know if you expect the response in that sector.
Yeah, so in terms of actual products, so most of them have most products at a broad scale, like what we're talking about, durable goods, have very low energy as a fraction of their total cost. Now, for some products, that's not the case, right? If you were talking to somebody who runs an aluminum smelter, that is, people probably know the way that you make aluminum is you take bauxite and electricity, right? I mean, it's incredibly energy intensive. So for some products, there's a bigger impact. And so for aluminum smelting, right, that's a sector where people worry if the U.S. adopts one of these taxes, that people will go to Quebec or other places to smelt their aluminum.
I kind of go along with that, and even your earlier point about the effect that electrical consumption, more or less, it did follow that 3% growth, our GDP went up. I feel like the whole assumption of saying that was due to price is a little bit reach. A lot of it is due to the fact that the steel beam that was bought for the COE increases our GDP, but it's made in China. So of course in 1970, manufacturing started depleting America, and so I think a lot of our electrical reduction you see from 1970 can probably be more attributed to energy efficiency standards and movement of manufacturing due to cost. Going along a little bit with that is my point of how do you take into account kind of what you're saying, not only aluminum smelting like in the North Country, New York, moving to Canada, but like all manufacturing not staying in America. Like, did you look at maybe implementing a tariff on, like a carbon tariff on goods that are made over in third world countries where this, they're able to make goods so much cheaper because they don't have to pay a carbon tax?
Yeah, so lots of good questions there. So it's true that a lot of other stuff went on in the economy. Okay, but some of those things happened because of energy prices, right? So you're right that this is not a clean experiment. This is as close as we get. It's an event that came along that people didn't expect, and that was initiated for reasons other than understanding energy efficiency. So we're doing the best we can. And there were other things that were going on at the same time. But some of those things, like energy efficiency standards, we have those because of this event, right? That was right. It was a response to prices. It was a national emergency. So, and the same is true with some of the manufacturing, right? So some manufacturing moved because of people paying attention to energy prices. So now it's true that that U.S. Consumption, when you measure U.S. consumption goods, you should probably take into account that some of the products are made overseas in a more carbon-intensive way. And so so what I showed you was U.S. energy consumption, but the U.S. carbon footprint, taking into account international connections, is not as optimistic. So you're right about that. In terms of carbon tax applied on imports, as a matter of fact, that is another paper that we wrote, and I don't have the slides with me. But one of the things that people have talked about a lot, and with the carbon tax, is whether there should be a border adjustment that adjusts goods from other countries for their carbon intensity. And we've looked at that, and one of the interesting things about that is that it generates a boatload of additional revenue, right? That in terms of thinking about tax reform, it provides quite a bit of additional revenue, especially as you go out into the future, unless you think other economies, especially China, are going to bring down their emissions a lot. So that's a good question, and people are working on that.
We're coming for the end. We can have another couple questions. I just want to say we've got
From the web.
Okay, so we've got maybe eight or so folks who've been listening on the webinar. So for folks on the webinar, if you have questions, use the chat box and you'll come into the room. So we'll get another couple of questions and we'll wrap up.
Is this work published someplace so that other people can have access to it?
Yeah, this is from a paper in the National Tax Journal. And so I'll give you a copy of my card and I can send you a copy of it if you like. This is published. The thing that on border taxes is not published because we're just finishing that up now.
What do you see as being the main barriers to implementation should politicians support something like this at the federal level?
Well, that's a good question, and it turns out that the barriers are really low. In lots of pollution control, like I mentioned at the beginning, that this is easy to measure, and from an environmental economics perspective, that's a big deal. Like a lot of the pollutants that we worry about, like NOx coming out of power plants and other stacks, there are lots of things that people can do that change the amount of NOx that comes out, and so you have to monitor emissions, and that's expensive. Here, it's easier. This is essentially going to be implemented like a sales tax, and at the federal level, actually, the U.S. has got a well-oiled set of institutions for implementing excise and sales taxes. In fact, I have a colleague who says that this should be a U.S. export. We should go around the world explaining how to implement these things in a low-cost way, because it's really pretty easy to do. That's part of the attraction.
So you're envisioning this being implemented as a sort of source point as opposed to
Yes.
the exhaust point? I'm
That's
thinking
right.
specifically of an initiative that NYSERDA used, measuring emissions at the exhaust point, and it's really hurt biomass investment and development in the state. And they weren't seeing it as a carbon neutral source because they weren't factoring in that this carbon was sequestered by trees. So.
Well, so there's two parts to that are important. So one is that measuring it upstream, right, at the point where the fuel comes into the economy, where it's imported or mined, is a lot easier because there are only a few thousand companies that would be subject to the tax, and a small number of places where you'd actually have to monitor it. But you'd be taxing the fuel, and sometimes people think it would be better to tax combustion of the fuel. That makes it easier to deal with feedstock uses of natural gas, among other things. But taxing combustion is really hard because there are millions of people downstream in gas stations and everything else. So it's harder to implement. And then it also is subject to miscalculating what's going on. So the carbon intensity of biomass, as you may know, is a fiercely contested, bitter subject, right? Which EPA has been wrestling with itself for about 6 or 7 years. And so for those of you who haven't really thought about this, on one hand, if you burn biomass, if you burn a tree, the tree, if it was a fast-growing pine in the south, it took the carbon out of the atmosphere the last couple of years, you burn it, you re-release the carbon, it kind of looks like a wash. On the other hand, if you burn other things, it may take many, many years for them to regrow. And so it's not so clear that what you're doing really is neutral. But if you burn waste, right? So I want to ask if you're from ESF, but ESF does a lot of work on burning wood waste and other kinds of waste. And that's a freebie because that would just biodegrade. A lot of it would turn into methane, which is a greenhouse gas. And so that should be, in the grand scheme of things, that should have a negative, that should be zero. Or if you're thinking about landfill gases, it actually should get a subsidy for burning that. But it's complicated.
Okay, so I want to thank our speakers and thank our moderators. Thank you all for joining us. If you haven't done this with us before, there are refreshments outside. I'd like to say that these events spark collisions, people that haven't met before. So come and meet somebody that you haven't met before and find out something new. So welcome.